We want this to be a new triangle. So we're used to going, 31 and 2, we're used to going 45 and 1 and 1, yeah? And I purposely didn't finish off and just quick as anything on that sort of stuff. We want a triangle that's got a 5 and a 12. So if I made that look reasonable, there's the 5, there's the 12. This triangle trick, I could talk about all sorts of whys, turns out to be really nice for solving this type of question. Okay? Remember yesterday, if we had something like sine 3x plus a sine x, no, it was times, wasn't it? Times by sine x, and we could turn that into a sine 2x using the weirdo formulas. So this is another trick that only works for this type of question. A right angle triangle with 5 and 12, and we want a 13 because of Pythagoras. So what's the trick? I want this to be a 5 on the 13, because if I look at this triangle and I look at, say, that angle there, I've got a 5 on the 13, which I'll call a cos. You right? So I want to get a 5. Why? I just want to pull out of the air. Now here's the interesting part, me and like equals off times 1. What we're actually doing is that. So if I times the bottom of that by 13, I've got to times the bottom of that. How many times? Well, that's right. I times the bottom by 13. So then I'd have to times the top by 13. So if I times that by 13, I've still got the cos, I've still got the sine, and I go, what have I done to the question? Then I need a 13 out there to make up for it. So I'm using those two numbers, I make them a right angle triangle, I work out the hypotenuse, and then I say, well, okay, I want to have 13 on the bottom of those two fractions, and to make up for that fact, I have to put another 13 here. Why? And why don't I go 3 times by another 13? Because didn't I times this side by 13?
Times by 1.
So, yeah, we went around in circles on purpose. And then you've got to say, what's this? We're back to what do I call it? An abab. So this one's going to become the cos, and this one's going to become the sine. Now, for various reasons, it's nice if we write that first and we write that second. It's a nice habit to get into. We write that first and we write that second. Makes the question turn out nicer. So I write that at the front, that at the back. You're okay with that? That at the front, that at the back. Like 2 times 3 is the same as 3 times 2. So now we've got a 13. We've got a cos x. Now, is this going to be cos, sine, sine? Yes. So what's our possibility for abab?
Why is it cos, sine, sine?
Well, I could go cos, sine, couldn't I? And I could go sine, cos.
Oh, because that equals the cos.
Yes.
Why is it a cos? Wait.
Oh, I know. Let's go back to abab. So you're saying why? Let's look at abab for a second. Cos of A plus B is what?
Is cos A...
Yeah, forget about the A's and B's for a moment. Cos,
Cos, sine,
sine, sine with a minus. You go, oh, wait a minute, we didn't have a minus there, we want a plus there. So if I had cos A minus B, which I did on purpose, we'd have cos.
But are you going from that second thing to
Oh,
the
yeah,
first
yeah,
one?
yeah.
Oh, okay, because I was like, where
I'm going
did you
from
get
there
cos from?
back to there.
Okay, cool.
So I wrote the rule up so you could see it backwards. So yes, it was going backwards.
Because I was like,
Yeah,
that's not...
yeah that's still right. Too.
Okay.
So what have I got? Oh, by the way, what do I do? I don't want to think. Wherever possible, I don't want to think about it. So when I see there, I just go cos, sine, sine. So this one here is actually multiplied by the cos of another angle. And most people call it alpha for some reason. Sine x, and we'll call that then the sine of alpha equals 3. And what have I got?
Oh.
Cos alpha equals 5 on 13. Can someone pick up their calculator? It'll probably be decent. And get me that answer straight to 1 decimal place. This is alpha equals running out of room.
67.4.
67.4. Now go back over to here, and now we've got sine alpha equals what? 12 on 13. Can you get that one for me?
Yup. 67.4.
So you know when we go, come up here, B, A, B, A, B, we want those two to be the same. So there they are, the first two are the x's.
Yeah.
And we want the last two to be the same. There they are, they're alpha. And alpha turned out the same for both of them.
That's fabulous.
Yeah, it is
It's also
fabulous.
horrifying.
Yeah.
Why would you do that?
Well, when we get quicker at it, you start to see a reason it's a nice way to solve it. So now we have 13 outside of cos x, cos 67.4. We're writing it really longhand, and I'm going to go through the whole thing, sin x, sine. And I'm expecting you to concentrate for too long. I got that, haven't I? So what can I do now? That's an abab. Do it in reverse. Which abab?
Disgusting.
So it's a 13 cos of what? A gets written first, B gets written second. Cos does the opposite of what we think, so it's going to have a minus. That gets written first, that gets written second, and that equals 3. Yeah?
If you were to keep it so that the 5 and 13 was in front of the cos x back here, would that stop up the question?
If we left it there like that.
In front, yeah.
Nah. So what do you do to solve that now? We're back to solving equations. And they said they want the answers only between 0 and 360. So why we for starters doing this, is if I got that question, there's this funny little technique. If I times that by 13 on 13, I can turn it into that using what we call that. Yeah? So what do we do now? We go the cos of x minus 67.4 is 3 on 13. So what do you do to solve that now? We're back to solving equations. And they said they want the answers only between 0 and 360. So why we for starters doing this, is if I got that question, there's this funny little technique. If I times that by 13 on 13, I can turn it into that using what we call that. Yeah? So what do we do now? We go the cos of x minus 67.4 is 3 on 13. Peekaboo method, I don't want to think about that. So Ethan, can you tell me the x value? That will give me 3 on 13 for cos. How do I do that? Instead of saying get cos 37, you're saying get me the angle. So inverse cos of 3 on 13. That's all we're saying. Why do I cover that over? Why is my whole teaching style go to this cover over method? Because when it looks more complicated, people think crazy. Angle is?
76.7.
76.7. It's a positive. Then you got to check. All stations, I call all stations central. Yeah? You go, where is a cos positive? There it is, it's positive there. It's negative there, it's negative there. And we're going to use an angle of 76.7 up there. And we're going to use an angle of 76.7 down there. So what's the next angle?
283.
360 subtract 76.7.
283.3.
283, and you'd already done from the angle.
Yeah.
So x minus 67.4, what is that? Feels so much more complicated. Funny when I'm explaining things when it feels like it's just really complicated. It feels unnecessarily complicated. But what I do know, if I come back and do it again tomorrow, and suddenly you go, why did you say that yesterday? That was really easy. So now, you're going to add 67.4. We've got a problem. Have we got a problem or not? Ethan, add 67.4 to that, please, Mr. Calculator Man.
When did I look? Yeah, 144.1.
0.1 degrees.
That's 350.7.
Oh, we just made. I just want to talk about for a moment. If I went and put that on my calculator right now and said graph it, guess what the amplitude of this graph will end up being? This is a really weird, lovable, fantastic thing. Weird, lovable, fantastic thing. What's Pythagoras for 5 and 12? So if I drew this graph up, it goes up to 13 and down to 13. go up and down 13? And then it did my head in, so I started going, what if I had 2 cos x plus 3 sin x? And okay, that's, I don't know, so it's 2. And or I just said, draw this graph. How far does it go up and down to? 2 2s are 4. 3 3s are 9. Gosh, I'm up to 13. So this thing has an amplitude, not a 13, what's it have an amplitude of? So you could pick up your calculator and put that in your calculator and see, oh, look at that. Yeah? Or if I made it, no, it's a stupid one, like cos x minus 10 sin x. By the way, if this graph goes up and down to 10, if I drew that, and this graph goes up and down to 1, will that have all that much of an effect? This will be more dominant. So if I do Pythagoras for that, 1 times 1 is? 10 times 10 is? So I've got an amplitude this time of 101 with a square root. Which is, by the way, what's that? About 10.1. So that didn't have much effect on that, which is a bit of common sense to talk about. We talked